In example 1, we discovered that as the number of compounding periods is increased, the amount in the account will also increase. This is intuitive, this is logical, because as we compound more frequently, we're compounding interest based on principal plus the additional interest. So it's that interest on interest that I talked about earlier. But it's true, though, that as the number of compounding periods increases infinitely, there is actually a limit or a ceiling to the amount in the account. So let's look at just a little discovery here, a little exploration of this. Let's say you invest $1 for 1 year, and we're just picking those as easy numbers that make this easier to look at and easier to compare. So we'll invest $1 for 1 year. So that means if our investment of $1, that's our P is 1, and our 1 year, that means T is also 1. So if I substitute into my compound interest formula, if I put a 1 in for the principal, P, and I put a 1 in for the T, here are the two 1s, this expression will simplify into 1 plus r over n to the n. So the amount in the account will be 1 plus r over n to the n. Now here's this quantity in this table. Along the left side, we have different interest rates. So here's 5%, 10%, 15%, etc. And then across the top, we've got number of compounding periods. So we're going from 100 compounding periods per year to 1,000 to 10,000. But the idea is that they're increasing, and we would increase infinitely. But what you want to look at is as you increase, let's say at the 5%, as we increase from 100 compounding periods to 1,000 compounding periods, you can see the difference is negligible. It's out to the, what is it, tenths, hundredths, thousandths, 10,000ths, 100,000ths place that this even differs. And then as you go from the 1,000 compounding periods to 10,000 compounding periods, again, negligible difference here. What you also want to see is over on the right. If R is 5, if you got a 5% interest rate, remember the number E, that 2.71, etc., e to the r power, so in this case e to the 0.05 power is 1.0512711, which again is very, again, negligibly different than these. So you can do that across all of these. So the difference as you go across with an interest rate of 10%, r equals 10, negligible difference as the compounding periods increase from 100 to 1,000 to 10,000, and once again, that happens to be equivalent, or almost nearly equivalent to, e to the r power. So we can see then that as n approaches infinity, as the number of compounding periods increases and gets larger and larger and larger, the amount in the account actually approaches e, that number e, 2.718, etc., to the r power. And when the number of compounding periods increases infinitely, this is called continuously compounded interest. And this is our continuously compounded interest formula. A equals P times e to the RT. So again, P is the principal, E is that number E, and we can use the calculator button, the E button on our calculator when we want to approximate this. R is still our interest rate, our annual interest rate in decimal form, and T is still our time in years. So you want to memorize, you want to learn your compound interest formula, your P times 1 plus R over N to the NT, and A equals P times E to the RT. So you need to know your regular compound interest formula and your continuously compounded interest formula.